All right, everyone. Hello and welcome back. So we are finishing up the second part of lesson number 7, so dealing with logistic regression. So where we left off last class is with this exercise here. So let's just recap on this for a second in case you forgot about it. So let's suppose you are a marketing analysis for an e-commerce company. Your goal is to understand and predict whether a visitor will convert. So again, make a purchase, not make a purchase based upon their behavior and source. So what we're going to do here is we're going to simulate some data. There we go. There is going to be 4 predictor variables and 1 response. So our predictor variables are first one, time on site. So this is going to be recorded in minutes. So how long did they spend on the website? Prior visits, have they been there before? So this is going to be count data. Device type, how are they connecting? Is it a mobile device? Is it a desktop? Campaign source, so how did they hear about this? Is it through email, ad, referral? And last but not least, the response, which is converted, which is just 1 or 0. So 1 if they did make a purchase, 0 otherwise. So we're going to simulate this data. We're going to put it into a data frame. And then what we're going to do, this first part here, is we're going to fit a logistic regression model with all the predictors to predict converted. So again, converted being our response. So we want to report coefficient estimates, odds, ratio, and give business interpretations for, we'll say in this case, 2 of the predictor variables. All right, so before we jump into the R part of this, let's just go on to the next slide here and just talk about some of what we're looking to accomplish. So the first thing that we really want to be able to accomplish once we already build the model, and we talked about building the model last time and how we interpret those coefficients. That was that maximum likelihood. Again, I'm never going to ask you about that. Just wanted you to be able to see that for a quick second as to how those come up, because it is vastly different than the least squares method that we were dealing with beforehand. So you have a general idea now. Perfect. If you want, there's tons of videos out there that go into much greater detail about that. Not the point of this course. But once we have that model, what we're looking to do is interpret the coefficients, the estimates that we get. So how do we do that? Well, the logistic model uses the logit function. Again, that's the one we're going to be focusing on. There's the probit one, but we're going to be using the logit one because, again, it relates better to, or it relates to odds, where the other one does not. So we use the logit function, and it can be written as follows. So remember, the logit of our response that we are looking for is the log of the odds, which if we just have a single predictor variable, this is beta naught plus beta 1x. So we'll keep this as just one predictor variable to help explain this, but again, this works for any number of them. So when we do come up with our estimate, so if we build our model, we're coming up for an estimate for beta naught, which is going to be our b naught. We need an estimate for beta 1, which is going to be our b1. Now, if we look at how it is outlined here on the right-hand side, this is additive, which means if I increase x by 1, the log odds, and that's the key part here, the log odds increases by beta 1, or in this case, our estimate of that, which is b1. So for every increase of x, we see b1 as the direct effect of that. So if it's positive, it's going up. If it's negative, it's going down. But this affects the log of the odds. That's a little bit harder to understand. Odds is easy to understand because that's the ratio of probability of success to the probability of failure. But here what we're talking about is not that. We're talking about the log of the odds. So it's not necessarily as easy to be able to interpret. So what can we do? Well, we can get rid of the log part of this. So we want the log gone. In order to get rid of log, and remember when I'm talking about log, I'm talking about the natural logarithm, so I'm really talking about ln. To get rid of that, I can take e to both sides. And if I take e to both sides, well, I end up with just the odds, and this is equal to e to the power beta naught, so again, our intercept, times e to the beta 1 raised to the power x. So x now becomes an exponent, so it's multiplicative. So if x becomes 1, then we have the odds change. So I should write this down here. If x is equal to 1, odds change by e to the beta 1. So really we have 3 possible outcomes. If e to the beta 1 is equal to 1, well, that means we're just multiplying by 1. There is no change. And if there is no change, this is the same thing as saying beta 1 is equal to 0. which when we were assessing the model beforehand, if when we're doing the hypothesis test, we were checking whether or not this was in fact equal to 0. So the same idea, if we get e to the beta gives us 1, well then that's exactly the same thing as nothing is changing in our model. We don't even really need to have it in there. Now the other two outcomes here is if e to the beta 1 is greater than 1. If it's greater than 1, then we see a percent increase. So for example, if it was 1.25, the difference between that and 1 is the 0.25. As a percent, that's a 25% increase. Now, if e to the beta 1 is less than 1, say a 0.75, again, that difference, or even say a 0.7, that difference between that 0.7 to the 1 is a 0.3, or as a percent, that's a 30% decrease now. So if it's less than 1, we see a multiplicative decrease. If it's greater than 1, a multiplicative increase. But it's changing the odds multiplicatively. So this is kind of what I have in the note here. So as x increases by 1 unit, the log odds increase by an amount of beta 1. Again, that's if we leave it in terms of that. Alternatively, if x increases by 1 unit, the odds increase by a factor of e to the beta 1. So again, 1 is additive, 1 is multiplicative. It's just when we're dealing with the odds, it's easier to keep things multiplicative because it's easy to be able to understand and interpret from there. So if x can only take on values 0 and 1, again, it doesn't necessarily need to do that, but just for the point of understanding this, if it can only take on those two values, consider it's either there or it's not there. So if it's not there in terms of the model, then again, that x being 0, well, that's just e to the beta 1 all to the power 0. Well, that's just 1. It doesn't change anything. It's like multiply. It's exactly the same as multiplying by 1. Nothing changes in the model. But when it is there, so when x is equal to 1, well, how does that model change? That changes by e to the beta 1. So this is what's known as the odds ratio. So the odds ratio is just e to the beta j, where j could be whatever one of our predictors are going to be. So it's how is it changing multiplicatively? Again, we're just taking e to whatever that estimate is. Now, of course, each one of these does in fact have a confidence interval. So if we find out that our beta is not equal to 0 through our hypothesis test, again, we've talked about that already, or we will talk about that again shortly. Getting my things confused. We just finished up with the Poisson regression. But yeah, if we find out that we want to keep that parameter or that predictor inside of there, then we want to find out, once we have the estimate, well, where's the true value going to lie? We could do a confidence interval using the confint function. Again, really no difference than what we've done already up to this point in time. So it's going to take whatever our estimate is, that b sub j, and we're going to go a little bit to the left, we're going to go a little bit to the right, and we're going to be, say, 95% or whatever alpha is going to be confident that the true population parameter lies within there. All right, so let's go through exercise 1 here. So I need R, so let's just change up my screen. And I do have everything already loaded here. So the first thing that we need to do is to generate the data. So since we're randomly creating things, again, we want to set a seed, so the data that you have is exactly the same as I have. So I'm using the set.seed, setting that equal to 42. Now we're going to generate 1,000 data sets, or data points, so n is equal to 1,000. So time on site. So this is going to come from a normal distribution, and I'm going to say the mean is going to be 5, the standard deviation is going to be 2. So our norm generates n, in this case 1,000 random data points with a mean of 5 and a standard deviation of 2. And we're storing that in the variable time on site. All right, so the prior visits, this is a count data, so this is Poisson. So again, I'm using the rPois for the generating function. I am using n being the 1,000 for 1,000 points, and I want lambda, in this case, the average is going to be 2. So what's the average number of visits? Well, the average is 2. All right, mobile device. Right, so this is just going to generate zeros and ones using a binomial distribution with a probability of success setting it at 60%. And last but not least, campaign, it's going to be email, add, or referral. We want to be able to sample this 1,000 times, and with replacement is true. So there we go. Perfect. So everything is built in there. At least I have my 4 vectors are all built in there. Now I want to build the response. So this is typically not what is normally done. Again, we don't normally start off by just generating the data. We already have this data, and we try to understand what the underlying model is going to be. Here we're going to create what that underlying model is, generate the data, and then from there, basically try and see how close we can get back to that original one. So here, what I'm trying to do next is I'm going to use Ada. So this is my linear combination of predictors. I'm going to say my intercept is going to be -2 plus 0.3 times time on site plus 0.5 times, this is going to be prior visits, then we got plus 0.7 times, this is the device. Device. And what else do I have here? Go back over to my other screen. Where did my mouse go? I can never find this mouse. Device under mobile. Whoops. Let's see. Okay, and this last little part here is if it is plus, it's going to be a 0.2 we're adding on if it's coming from a add, and it's going to be minus 0.1 if it's coming from a referral. I'll just leave it like that. Hopefully you can see this. Let me just switch over to my other screen here just for a second, make this a little bit bigger. But that's basically the underlying formula for the linear combination. This is what we're getting as Ada. So I'm going to build a vector that is going to be made up in exactly this form. So again, the intercept being -2, then plus 0.3 times time on site. So we created a vector from that. So we're just multiplying that by 0.3 times 0.5 of the vector we created for prior visits times 0.75 for the device, whether it's mobile or it's not. That's a 0 or 1. And then last but not least, the addition of if it is going to be, or how the referral method or the campaign. So if it's email, if it's referral, or if it's ad. So if it's email, it's already built into the intercept. That's the -2. If it is referral, we're subtracting 1 from there. If it's an advertising, it's a 0.2. All right. So I'm going to now build this vector Ada. All right, so remember, this is the log of the odds. So that's exactly what we have. So we have log odds. I'll do this a little bigger here. So log odds is equal to Ada. So now I want to put this as P. I want to find what is the probability. So probability is, again, that was just odds over 1 plus odds. But I need to do things a little bit differently here because I don't have things in terms of odds. I have it in terms of log odds. So to find P, I'm going to do E to the odds over 1 plus E to the odds. Or sorry, not odds. Ada. There we go. So that's what I'm doing here. So that's line 44. So I'm building what is the probability of each one of these happening based upon the model that we've just created. And now what I want to do is I want to generate a response based upon these probabilities. So I'm going to use a binomial distribution. So it's only going to have values 0 and 1. I'm going to create, it's going to have only one single trial. I'm going to create 1,000 outcomes here. So a vector of size 1,000, which is just going to be zeros or ones. And it's all going to be based upon a probability p, which is what we just created above here. So this is going to be the vector converted. And now I'm going to put this all into a data frame I'm going to call df. Okay. So again, general idea of this is typically we would just have this data frame. We would not have all of the underlying structure that we have here, just the data frame. And based upon this data frame, I want to be able to create a model, and hopefully it should resemble what the true population parameters are going to be, which is exactly what we just outlined above here, because that is the formula. That is how we created everything. So that is the true model that we're trying to reproduce here. So can we do it based upon all of this? All right, so the first thing that we want to do is we want to fit the model. So I'm going to use on line 49. I'm going to call this full or model underscore full using GLM, our function, saying converted is explained by time on site, prior visits, device mobile, and campaign. The data frame is df, and the family is coming from binomial, and we're using the logit function. Now, I don't really need to put that last little bit in there, that link, because by default, it's automatically going to be the logit function. But for good practice, it's nice to have that in there. Okay, so we've now built a model based upon the data that we've just had. Now, how close is it to the true values here? Well, let's look at the summary. So here we have estimates. We'll just call this EST, and true. All right, so the estimates, and again, these are based upon log odds. So our intercept, the estimate for this is negative 2.075 approximately. Well, what's the true value of this? What is the true intercept based upon the model that we've created? Well, that's above. The true value is -2. So we've gotten really, really close to that. Prior visits, what was that? That is 0.35. The true value is 0.3. Again, based upon the model from above. Pretty accurate. Mobile device 0.6. Nope. Sorry, that was time on sites. Prior visits 0.55. True value is 0.5. Device mobile 0.68. 0.7 was the true value. Campaign email was negative 0.1. It's actually 0.2. And negative 0.27, negative 0.1. Okay. Now, one thing to note here, you might look at the last two going, well, they're not really as close as the other ones were. But if we're looking at the summary table right here, look at the estimates that are statistically significant, so that have incredibly low p-values. So everything that we would test, running a hypothesis test, based upon the p-values, well, the time on site, prior visits, device mobile, those all are statistically significant, even with an incredibly small alpha. But if we left alpha being 0.05, this would hold perfectly true, which is why when I'm looking at all of these, from here all the way down to here, these are really, really close to what the true values are going to be. Now, on the other hand, when I'm looking at campaign email, campaign referral, they're not as close, but they're not also as statistically significant, which means that looking at the difference between these two might add something to the model, but really not statistically significant enough. Okay, so that was the first part. What else is it asking me for here now? Because there was a couple of things that it was asking for. So I just want to make sure that I've covered everything correctly. All right, so we've got that. We've got the true value. What do I need now? The odds. So we've looked at the estimate, the odds ratio of each one of these. This is just taking e to that specific power. So if I took e for the intercept to the negative 2.075, this is going to get me 0.1 12556 approximately. And for the next one over, if I take e to the 0.35, this is going to get me approximately 1.41746, so on and so forth from there. Actually, let's do them all. So the next one is 1.72495. Then I have 1.98039. Then I have a 0.89865. And lastly, 0.7676. There we go. 386. All right, so all the ones above are greater than 1. So if I'm looking, say, at this one here, this is approximately a 42% increase. So that 0.35, that was time on site. So what that means, for each additional minute that they spend on the site, the odds increase by 42% that they are going to make a sale. So the longer they're on the website, the more those odds increase to the fact that they're going to be making a sale. Now, if we look at the other hand, these ones are less than 1. So this is approximately a, that's almost at a 0.9. So that is a 10% decrease. So if the campaign goes for email, so if that's how they get access to the, or they're referred to the website through email, then overall, if we keep other predictors constant, then we see a 10% decrease in whether or not they're going to do that. Okay. What else do we have here? Oops, that's there. Oh yeah, we're going to look at business interpretations of some of these. So let's just do one, and I'll leave one as an example for you folks here. Let's go over to the next screen. So let's just look at prior visits. All right. So the odds ratio is approximately 1.725. So this means, and I'll write this out, so sorry about my handwriting there, meaning that each additional visit to the website increases the odds of conversion by about 72%. Holding all else constant. All right, so the business takeaway: consumers who have visited before are substantially more likely to convert or make a purchase, so investing in remarketing to returning visitors has high leverage. So good return on investment in that case, if that's what we're looking to target. So if we can get people to come back, then there's a significant increase on the odds that they are going to in fact make a purchase. So whatever we can do to invest in that sort of remarketing campaign that gets them back to the website, the better off it is for us. All right, and I think that is everything from here. Where did my mouse go? Always losing my mouse, so let me just change my screen here so you can see this just for a second. So again, just prior visits. So the odd ratio again is that 1.725, which we've rounded out. The difference between that and 1 is about 0.73 or if we round down, we'll go to 72%. So again, each additional increase in visits is a 72% increase in the odds of it happening. There we go. What else do we have here? Now I do have in line 54. This just gives me what the odds ratio is. So again, that's just taking each one of those estimates and raising it to or taking E and raising it to each one of those estimates. So I kind of wrote those out by hand, but now they're here for you. As we can see, prior visits at 1.7249517. That's where we got that one from. And if I want to find the confidence interval, so again, same idea. The confidence interval for each one of these, if I just did the conf int of the full model, that would be for the log odds. And again, I can take E to both sides of these. And this is exactly what I get. I still get that percent increase or decrease based upon the odds ratio. So if I look at prior visits, the lower end of this at a 95% confidence is 1.526, so approximately 53%. So kind of a worst case scenario. If they come back to the website, 53% chance, or there's a 53% increase in the odds that they're going to make a sale, all the way up to 1.9601935, so a 96% increase. So massive reinvestment into that. Okay, so we've created the model, we've interpreted the coefficients and kind of what they mean by looking at the E to whatever, those odds ratios, because I want to know, how does the odds change? Come on, let's go switch up my screen here. There we go. All right, so once we've created the model, we've understood what the coefficients are. Now we ask the question, do they actually provide anything for us? So this is where we want to do that hypothesis test. So this is the Wald test. And it's the same as before. All we're simply doing is we're doing the hypothesis test saying, is the true population parameter, that beta sub j, is it equal to 0 versus the alternative? It's not equal to 0. So again, I don't care if it's positive or if it's negative. I just care whether or not it's not 0. So the test statistic of this, we can use we can do this with the z values, or we can actually calculate the Wald statistic in itself. Keep the z values. We automatically get this from the summary table. We already showed that it's just the square of that, so no big deal from there. We did bring this up slightly last time around in terms of the Poisson, how we could inflate if there's over dispersion. We don't really have to worry too much about over dispersion when we're talking about non-count data, but it's still an option to do in here, and we'll see that towards the end of the lecture. But again, for now, don't have to worry about that. In this case, the phi is just equal to 1 unless we determine that there is over dispersion and want to create a different model from there. All right. So if H naught is true, then Z follows approximately the standard normal distribution. So again, all of this falls into that summary table. And if we look at the summary table, we already quickly talked about this, when things are statistically significant versus when they're not. And it was really that last categorical variable that was statistically not as significant as everything else was. All right, so we might as well compute the Wald test, but we're only going to do it for one of the coefficients. We're going to stick with the prior visits on this one. All right. Oh no. Oh, this might be problematic here. Everything crashed on me for a second. Play from here. Good. Don't know why that crashed. I don't like that at all. But everything else is still recording and going. Okay, perfect. All right, so let's do this one. So first things first, we want to state the null and the alternative hypothesis. So the null hypothesis, whoops. H naught. And here we're talking about beta, and we'll put this as prior visits, or PV for short. So that is equal to 0. That is our null hypothesis, so it's adding nothing to the model, which again is the same thing as E to BV is equal to 1. Because E to the 0 is 1. So there we go. Versus the alternative, HA, which is B, PV is not equal to 0. So it's adding something to the model. Either increasing or decreasing, but that's it. All right, so our alpha here, because it doesn't state, oh no, it does state 0.05. And our p-value, from the data that we have, and going back over to R to be able to quickly pull this off again. Prior visits was 2e to the negative 16, which is approximately 0. All right, so our alpha, probability of the type 1 error, so rejecting the null hypothesis when the null hypothesis is in fact true, we're going to do that 5% of the time. What is the probability that we would see such a test statistic of, in this case, the test statistic for the prior visits is 8.549. What is the probability that we would see that or larger? Well, it's approximately 0. It's so incredibly small. So since the p-value is less than alpha, reject H naught and accept HA. Thus at alpha 0.05. Prior visits should be in the model. There we go. And of course, we would want to do this for all of our estimates inside of there. Excellent. All right, so again, wald test, great for individuals. We can quickly look at the p-values from the summary table and determine whether or not we should add things, or whether or not we should remove things. But remember, we can't do things. I will get to this. We can't do this simultaneously. So if I see a couple of predictor variables that estimates have very, very high p-values, I can't remove them simultaneously because, again, this is done for each individual. But same as before, we have that drop in deviance test that if I have a model and a submodel, so a reduced model and a full model, where one is contained in the other, we can check that whether or not those additional extra predictors that we have added on contribute to the model in itself. All right, so consider comparing two nested generalized linear models. So again, model A would be the nested, model B would be the full. So they both go up to x sub k, so there's k different parameters inside of there. But then that goes from k all the way up to kb. All right, so we're asking, are those additional parameters or population parameters equal to 0? So the null hypothesis is the reduced model is already good enough. I don't need anything else from there. Versus the alternative that at least one of those additional predictors is statistically adding something to the model. So at least one of them is non-zero. We don't know which one, but at least one of them is in fact non-zero. So when the reduced model is true, the drop in deviance is going to follow a chi-squared distribution, where D is going to be the degrees of freedom, which is the difference in the number of predictor variables for the two models. So again, same as before, we can use the function to be able to do this. I do not need to be able to calculate these both by hand, but I could if I wanted to. So the additional parameters adding on, of course, there is going to be a drop in deviance no matter what. But we were asking the question now, is it statistically significant? So the null hypothesis is the reduced model is the better model. So what I need to see is a large enough drop in deviance to say, well, wait a second, that drop is more than what would just happen at random. Therefore, it's probably not true that all of these additional predictors are truly zero. At least one of them is contributing something to the model. All right, so we want to conduct a drop in deviance test. We want to compare the full model to the reduced model with only time on site prior visits. So I have two parameters in there out of the four. So we want to state the hypothesis, test statistic, p-value, and business conclusions from here. Nice and easy, eh? Let me just try this again. Where in the world did my mouse go? All right, so I have this set up. This is fine here. This is fine here. So let's do this here. Okay, so let's just start writing this out. So reduced model, or red model, reduced. This is converted, is explained by time on site. I'll just leave it as time plus prior visits. And the full model is everything that it was before. So converted is explained by time prior plus device plus campaign. There we go. So our hypothesis, H naught, is that, well, what are the additional variables that are added on here from the reduced to the full? So that is device is equal to campaign, which is equal to 0. So the alternative here is at least one of them is in fact not 0. All right, so what do we need to do now? Now we need to go over to our, again, I lost my mouse, keep losing my mouse. Let's switch this up here, change up the screens, perfect. What do I have here? So from line 57, and I'll leave this for you folks to play around with, to line 64, all we've done here is calculated the walled values by hand. Or not by hand, R did it. The formulas for R are inside of here. Specifically for time on site and showing that it matches up exactly with what we have in the summary table. So I'm not going to go through all that because all the information is in the summary table, but if you want to do that and see exactly where all that's coming from, that is, again, starting at line 57 going all the way up to 64. All right. So we built the full model. Now I'm going to build the reduced model. So again, using the GLM function, converted is explained by time on site and prior visits. Everything else stays the same. Now that I have those two models built, now we're going to use the ANOVA function. So the reduced model goes in first, full model goes in second, and just make sure that you set the test to chi-squared. All right, so I've got all the information here. So it says my drop in deviance. It's dropping by 22.966, and the p-value, the probability of seeing this given the null hypothesis being true, which is these added on give me absolutely nothing, is 4.104 e to the -5. So again, taking that decimal spot, shifting it to the left, 5 spots over gives me an incredibly small number, well past that threshold for cutoff. So let me just go back here to my other screen. So deviance difference is 22.966. The degrees of freedom Well, the degrees of freedom are 3. Why are they 3 in this case? Because it's only the difference between two parameters. But remember, one of those is a categorical variable. So this also includes the dummy variables. So since there's 3 levels of that categorical variable, it's going to have 2 dummy variables. So 2 from campaign plus device gives me my 3. So my degrees of freedom is 3. All right, and the p-value is approximately equal to 0, which is less than alpha, which is 0.05. So we reject H naught, accept the alternative, and thus the full model fits significantly better. Trying to write on this pad, I've never gotten used to this. All right, so what does that mean in terms of business conclusions? Well, it means the following. So if we include device mobile and campaign as predictors, there is, or as predictors, including them as predictors, significantly improves the ability to predict the, why am I having so much trouble talking today? Customer conversion beyond just time on site and prior visits. There we go. So this means device type and campaign source carry additional actionable information. So marketing efforts should be, think of this as segmented or optimized by device and campaign. So if we could prioritize mobile experience improvements, that might be helpful overall, and different efficiencies for campaign sources to increase conversions. There we go. So they are adding something, so we may want to focus on making those things better. If they weren't adding anything to it, then, you know, fixing up the mobile website might not be a huge major thing that you want to spend a lot of money on. Same with campaigns. If the specific way in which the information is reached to the consumer, if that did matter, again, we wouldn't want to waste too much time or effort in that direction. Whereas prior visits, we already saw it. That is a major selling factor to increase the odds of something happening or the odds of a conversion happening. So that's definitely something we want to invest in to make that experience better, or not just make that experience better, but in order to re-attract those customers back to the website constantly. Okay. Where did my mouse go? Here we go. Sorry, I did the solution on the other ones. All right, so goodness of fit test, same as before. The goodness of fit test uses deviance, or using deviance evaluates whether the model fits the data well. This test uses the deviance statistic to compare the fitted model to the saturated model, a model that perfectly fits the data. So if we had all of the data points inside of there and a variable for each one of those, we could hit it perfectly. That would be the saturated model. So how close are we to that? So H naught, again, that null hypothesis, the model fits the data well. The alternative, it does not fit. So in this case, actually, we're not looking to reject the null hypothesis, because the null hypothesis is the model fits the data well. So unless there is something inherently wrong, we're missing predictor variables, there is over dispersion, so one of the assumptions is not properly met, we do want to be able to deal with that from there. All right, so assuming the null hypothesis is true, the deviance statistic follows, again, a chi-squared distribution with degrees of freedom equal to the number of observations minus the number of parameters in the model. This also includes the intercept. Our rejection region, if the deviance statistic is large, greater than the critical value from the chi-square distribution, we reject the null hypothesis, indicating that the model does not fit the data well. All right, so what we want to do now is we want to perform a goodness of fit test on this. Same as before. So let's jump back over. All right, so I'm going to grab the deviance, or sorry, the degrees of freedom for the full model. and I'm going to grab the deviance from that. So what I'm going to do now is I'm going to find what is that critical value. So alpha being 0.05, I want to be able to find what is that cutoff point where 95% of my data is to the left. So if I'm doing this, what is the expected deviance I should be getting where 95% of the observations when the null hypothesis is true is to the left of that, based upon the degrees of freedom from the model. Okay. Now let's calculate the p-value. So what is the probability that, again, we ran this experiment over and over and over again, that I would see the deviance that we have here or larger, based upon, again, the degrees of freedom. So our critical value is 1086.458. But what's the deviance from our model? Our deviance from our model, 1049.2. Okay, so 1049.2 is to the left. It's very, very close, but it's to the left of that. So what is the probability that we would see this level of deviance? So again, what's the probability that we'd see 1049.2 if the null hypothesis was in fact true? We would see that almost 11% of the time, or 10.9404% of the time. So a lot of the time, not a lot of the time, well, 10% of the time, it's still often enough. So for us to be able to see a deviance of this or larger, to be able to reject that null hypothesis has to be less than 5%. Here it's 10%. It's not in that rejection region. So based upon the p-value, we fail to reject the null hypothesis. Based upon the critical value, we fail to reject the null hypothesis. So again, what is the null hypothesis? In this case is the model is a good fit. So I have no indication here that overdispersion or something like that, or one of the model assumptions have in fact been violated. Now, of course, same as before, we could look at the ratio between the residual deviance and the degrees of freedom. And if it's vastly different than one, then we run into a problem. So right now I'm looking at this. The difference between the two, the dispersion is 1.055486. When we're up the 1.2 region or 0.8 region, that's when we probably should be looking at this a little bit more closely. But right now, it's very, very close to 1. We looked at the test, and again, we failed to reject that null hypothesis. All right. 2 last little things to go, and we're almost done because we're at 47 minutes. Holy geez, time flies when you're having fun with stats. Yeah! Same thing as before, predicting new observations. So when we go through this process and we use the predict function, same as before with Poisson, we have to indicate the type that we're looking for in this is response, because otherwise when we do this prediction, what it does is it gives us our log odds, that eta. So the log odds, and then it's going to give me to the left and to the right of that, and that's not what I really want to be looking for. When I'm looking again for a confidence interval. When I look to predict, I want that actual value, and of course I want the confidence interval a little bit to the left, a little bit to the right of that. So in order to get that, again, I just have to make sure that the type is set to response. If it's not response, it's going to get me the log odds. If I put it to response, then it's going to get me the actual value in there. Now, if I want a confidence interval, there's another input that I want. I just have to put SE for that standard error.fit equals to true, and it will give it to me automatically. So I can't use like the conf_int function or anything like that. I have to use this code inside of here. All right, so let's suppose here that we have 2 customers, 2 hypothetical new visitors that had the following data. So for customer A, the time on site, they spent 2 minutes. Prior visits haven't been there there before. Device mobile is set to 1, and add was how they were able to find the website. Customer B, 7 minutes on the website, 5 prior visits, so that's solid. 0 in terms of the mobile device, and the email is the campaign that went from here. All right. So let's jump over to R. And first we need to create a data frame. So the data frame, remember, each one of those rows represents a customer. So row 1 will be customer A, row 2 will be customer B. So all the information needs to be put into there. So we're going to store that in new customers using the predict function. Now, first things first, I'm not going to set the type equal to response, and we're just going to take a look at this. All right, so using the predict, given the full model and the new customer data, what do we have here? I have values for the first one is negative 0.6939664. And for customer 2 or customer B, 2.986. Again, these are log odds. So what exactly do those mean? Well, again, it's hard to tell. I can figure out what the odds are by taking e to both sides. So just exponentiating both. So the odds of success is 0.499 and change. For the first one, for the second one, 19.81. Okay, that's big. So 19.81 to 1. So almost 20 times you're going to get a success. 1 time you're going to get a failure from there. Whereas the other one, you're more likely to get a failure than you are to get a success. Now, if I change these to probabilities, the probability that customer 1 makes a sale is about 33%. The probability of customer 2 making a sale or making a purchase is 95%. Okay, so big difference right there. So I can do all those calculations when I don't do the type equals to response. Or no, notice if I do type equals to response using the predict function, it automatically gives me those probabilities. Now I didn't put the standard error equals to, or what is it? Let's add that in here. So let's do it's equal to true. There we go. And if I run this, so now with those in there, what this does is it gives me the fitted values, and it also gives me the standard error. So it doesn't give me my upper and lower bound on it, but it gives me what my error is going to be, so I can determine what that upper and lower bound is going to be. All right. Okay, so we got all of that stuff. So customer A, so mobile user from ad campaign, low engagement, 2 minutes again prior, or 2 minutes on the website, no prior visits to the site. Log odds is about negative 0.694. And again, the predicted probability of a conversion is about 33%. So if we set the default threshold, if we're assuming that if we have a probability of 50% or higher, we can consider that a sale. We would classify this visitor, again, if that 0.5 was the threshold and we only got 0.33, we would classify this visitor as not converting. Customer B, on the other hand, desktop user from an email campaign, very engaged, 7 minutes, 5 prior visits, yielding a 95% conversion probability. So we would class this as a converter, someone who would in fact purchase. So what kind of business insights can we take from this? Well, first, visitor B is a high confidence target for immediate promotion or upsell. We know that we're going to get something, or there's a very, very strong probability that we're going to get something from there. So if we can upsell in some way, some promotion that we can combine in there to increase the sales, awesome. There's a strong likelihood of that. Now, visitor A, this is kind of borderline. So it's missing the conversion. So, or I should say, it's not missing. It's if we set the default being 0.5, and maybe 0.5 is not the right way of doing this, but if we do set it to 0.5, then we classify them as not making a purchase. So maybe from a business standpoint, if missing a conversion is costly, so we want them to be able to, we want to be able to increase that 33% up to a higher threshold. Well, how do we do that? Well, on top of, we might lower the threshold there. There might be some sort of incentives to nudge this type of customer. So we'd have to look at other factors as to why this customer ranges in this area. Are there other factors that we can influence to bring them up from a 33% to above a 50%, giving them more of a likelihood to in fact convert? So it's not just we're automatically writing them off. Like we may write them off, but at the same point in time, if losing out on that sale is massive, well, how can we change them? What can we do to influence them? All right. All right, and last but not least, we're going to come up with an example now of where overdispersion is going to be an issue. So we already did the goodness of fit test. We saw that it passed the goodness of fit test. We failed to reject the null hypothesis, so overdispersion didn't seem to be a problem. So again, overdispersion is the issue when that variance does not match up to what we are dealing with. Now, this is primarily dealing with count data. We don't run into it a huge amount when we're dealing with logistic regression. But it can come up, so we'll still go through the process of this. How do we do this? Still dealing with a quasi-binomial this time. So we just use the GLM function, and we just set the family to quasi-binomial. And that will set the that dispersion parameter, that phi, to something greater than 1, so it's going to reinflate that standard error. Again, this does not change the estimates. The estimates for the population parameters stay the same. The only thing that changes is we're reinflating that standard error, which is going to change the test statistic, which is going to change the p-value. So it's going to increase the test statistic, and it's going to lower the p-value. No, other way around. Decrease the test statistic, increase the p-value. There we go. All right, so let's go over an example here. All right, so we're going to generate a new set of data. So same example, except just different data. So my C is going to be 42, N is going to be 1,000. Again, I'm going to create from a normal distribution time on site, prior visits from a Poisson, device type coming from a binomial, and ad campaign is just going to be a categorical variable. My model is going to be exactly the same. Now what I'm going to do is I'm going to add some noise. This noise is going to come from a normal distribution with a mean of 0 and a standard deviation of 1.5. So I'm going to create my eta, again, that linear combination, taking the original base that I had and adding that extra noise, creating the probability of this, then creating the response, which is going to be that converted, and then I'm going to create my data frame, which is going to be df underscore over, so it's going to have the overdispersion already in there. So if I fit my model, and this time I'm just using the standard model, I'm not going to do the quasi-binomial. So if I do the full model, I hit the summary. Notice again that the first 4 estimates seem all statistically significant in terms of my summary. If I'm looking at those p-values, all of them seem good. But is anything different? Well, that residual deviance is different. So if I look at that ratio between that, which is what I have here, now I'm up to a 1.19, so almost a 1.2. That is a 1.2 if I round up. And as I said, once I hit this kind of threshold range, this is where I need to start paying a little bit of attention. So let's do a goodness of fit test, because again, a 1.2 might be perfectly fine, but let's test at a level of statistical significance here. So what is my residuals? Deviance, find my critical value, my p-value, and let's print this all out. So critical value is 1068.458, so it's exactly the same as what it was before, which again, my degrees of freedom isn't going to change, and it's based upon the degrees of freedom. My p-value, on the other hand, is 1.467 and change e to the negative 5. So again, taking that decimal spot, shifting it 5 spots to the left, so an incredibly small number. But remember here, the null hypothesis is the model is a good fit. So my p-value is small, I'm rejecting that null hypothesis. My alternative is the model is not a good fit. So we do have that overdispersion in there. So if I build a new model now, I'm going to call this model underscore quasi. I'm going to set the family into quasi-binomial. Everything else stays exactly the same. My summary, notice here it takes the dispersion parameter, which I have right here, being 1.01 and change. So this is going to be used to inflate the standard error. So again, it's going to decrease the test statistic, the t values here, and increase the p values. Now in this case, everything is still statistically significant, at least what it was beforehand, but is it as statistically significant? Well, let's look at device mobile. That's 0.00948. It was 0.00899. So it's gotten a little bit larger, not by much in this case. But mainly that also has to do with the dispersion parameter isn't really overly that high to begin with. It's very close to 1. But there we go. So that's how we do it. So if there is dispersion in there, we do our goodness of fit test. It will detect that as it has, and then we can do a quasi-binomial model, which is going to then allow us to kind of see how the changes in the standard error play into everything else. So again, this only affects hypothesis testing. All right, so let's wrap this up here because this was the last slide. So logistic regression gives us a principled way to look, or really a principled way to model binary outcomes. Again, that's 0 and 1 outcomes using the logit function. We've seen the probit function, but again, the logit function is nice because there is an easy interpretation of the estimates when we are looking at them in terms of the odds ratio. So it's e to whatever those estimates are going to be. Which are, again, in our case, easy to communicate in the business terms, because what is the odds? Again, probability of success to the probability of failure. So it's easy for me to say, well, the odds are increasing or decreasing multiplicatively by this amount here. We assess individual effects with the Wald test and compare nested models with the drop in deviance test. So if we're looking at individual parameters, the Wald test works perfectly fine. If we're looking at a group of predictor variables, then we have to do that drop in deviance test. When making decisions, again, at the end of the day, what is this giving us? Well, if we set that predict type equals the response, we're ending up with a probability. So what is the probability that we are going to get a success out of here? Again, we can label that as a 0 or 1, whether it's going to be a success or a failure, based upon some threshold. Now, again, when making that decision, we convert probabilities into classifications using thresholds, but those should really reflect business costs, not just use the default 0.5. So you need to take into other things into consideration. But that's it. That's all for logistic regression. So now the last thing that we're moving on to is the time series, and that'll be up in the next day or so. So we'll see you all back here in the next little bit. Yeah. Any questions, comments, concerns, feel free to reach out.